Hello guys, welcome to Wave paper reading channel. Today we're gonna be reading a paper which name is DiTAR, Diffusion Transformer Autoregressive Modeling for Speech Generation by ByteDance researchers. I believe you guys have been watching the previous video of ByteDance paper. It's Seed-TTS. It's like a technical report, but everybody is interested in the core technology it has because the paper didn't say too much about the network architecture and also what leads them to adopt the full diffusion, what do you call that? Non-cascaded system, which is the full diffusion transformer autoregressive modeling. And recently, they do put this work on their archive in February 2025. And this is why I chose this paper to see if we can get a better understanding how they come up with this method, DiTAR. All right. And for those of you who just saw this paper, you can definitely check. Not this. I want to show you the other one that I have. Right. The paper's title is anyways. I have to stick to this one. You can search this keyword in my channel, Wave paper reading channel. It's called Seed-TTS, and you will find the paper reading of this paper work. And today we're gonna start now. First of all, what it does, it leverages a divide and conquer strategy for patch generation, where the language model processes aggregate patch embeddings, and the diffusion transformer subsequently generates the next patch based on the output of the language model. It's not that straightforward for us, and let's take a look at their introduction. First of all, they discuss about the autoregressive language model. Everything they mention about AR means autoregressive. In comparison, they're saying that, okay, language modeling, especially for text modeling, people use discrete tokens, right? And when people working in speech signal other than text signal, they're different. Speech signal is more like a continuous signal. So this is why, according to the published results, continuous tokens can better reconstruct the original information. Why? My understanding is, or based on what the papers I've seen, is that if you're familiar with the wave 2 back 3.0 or Hubert wave LM papers, they're all about how to convert a sequence of continuous speech signal into a sequence of discretized tokens. And usually when they using these models, the purpose is either to run speech recognition or speech translation, speaker identification, these type of regression-based tasks. It's not for generation task, for example. They're not using that. The people that are using that for text-to-speech synthesis. But the issue is that you can think about for every frame of speech, for example, of 1 second of window, it has, if it is 16 kilohertz sample, it has 16,000 speech samples. And then that frame of speech can be turned into 1024 samples after passing through layers of transformers in the wave to back. And you can see there's an information compression over there. And the way that Hilbert or other wave to back models, what they do, people found that, okay, they only keep the coarse information of it. They throw away the fine-grained information in it. For example, well, there's no clear understanding what exactly fine-grained information was thrown away, but people try to use this information to go back to the speech signal during generation, right? They found, okay, the quality is not very impressive. This is why people want to address this challenge. So before this work, people usually like to have these two-stage strategies. Okay. They first have a lossy, right? Lossy discrete token is generated. Then it would take a token-based diffusion for detail enrichment. So they get this first, then they try to come up of enrichment, to get more information out of it. But this is through a diffusion model. And you can see this is a two-stage. The first stage is discretization. That's the first step. This is the second step. This is why it's called two-stage, right? Well, this is everybody can see that this design suffer from error accumulation and limited the scalability of the language model. And then also they talked about why they're using diffusion model in this work, because it received huge success in the image generation task. Also, they raised the issue, and people using diffusion model in speech before they publish the work, because for image you can definitely apply the causal attention, but for speech generation, everybody wants to have low latency. For image generation, you give them an image of cat, and then it's not streaming, right? You just give it the image and the patchification of it and use a causal attention model to work on this model, and that's it. But for speech, usually you don't have all the signal at the beginning, so at the time 1 second you only have access to this data, and at time 2 seconds you'll have this access to this segment, etc. So you have to use a non-causal attention language model, right? Or you have to wait till the end of the speech, which gives you large latency. Okay. So this is why they want to say, okay, I want to use diffusion model, but diffusion model per se or by itself it's not or cannot handle the non-causal input, okay, or attention. And how can I use autoregressive modeling? Because autoregressive modeling is causal in nature, right? Because it always tries to predict the next token and doesn't dependent on, it's not dependent on the future tokens, okay? Whether they can use autoregressive model, okay? So for this one, this is why they introduced their work, diffusion transformer, autoregressive modeling. There are some previous work, and the key thing they have done is shown here. First, they tried a patch-based autoregressive framework, okay, which blends the language model and the diffusion model. Secondly, they proposed a fast temperature-based sampling method. Frankly speaking, I don't think this is very new because they borrowed the idea from the image. But the first one is definitely new. And third is they apply this thing to zero-shot speech generation. So what is zero-shot speech generation? It's about giving a sequence of text. You want to synthesize the text, but you also give it a prompt, which is a voice prompt. For example, 10 seconds of audio of a specific person, and you tell your model that, okay, I want you to synthesize the content of the speech, content of the text in speech, but also in this specific person's voice. Okay, but you didn't provide any training samples of this target speaker. This is why it's called zero shot, and this is speech generation. Okay, and they're demonstrating this has much lower computational load, which means their system is fast, low latency, low computational cost, etc. Now we're gonna move quickly onto the related works. Well, this is a very nice written. Language models are primarily used for discrete representation, while diffusion excels in model continuous contribution, modeling continuous. These are related work. For you guys who are interested, you should read them. I just want to highlight something here. Well, the interesting thing is because you can see in nature, diffusion model requires or uses bidirectional modeling, and they create this a patchification idea or way to not only lower the computational demand, so they don't rely on the whole history, but they also enable the bidirectional model on the patches, which that's what the diffusion model wants the input to be. While the autoregressive model doesn't have this bidirectional thing, right? Zero-shot TTS, there are tons of people working on this topic. They're addressing the issues that people have because these models there can be categorized into two, multi-stage or single stage. I can see these ByteDance people are not in favor of multi-stage generation because they claim that these ones are usually, because it's a cascaded system. Imagine this, and then they say, okay, single stage method, okay, they just are focusing on one thing, which is generating high information continuous representation, which reduce the error propagation in the multi-stage method. Okay, let's jump to the method. Maybe most of you are interested in network architectures. I would say it's now very straightforward. First of all, they introduce the conceptual initiative of why they pick up the DiTAR, or how the formulation in general works. Okay, it is autoregressive. See this equation. They can use IID assumption to model the joint distribution as a multiplication of the conditional probabilities. Okay, because they assume that, okay, they're in a streaming mode or in a causal framework. Every sample of the speech is only dependent on the histories. So people that call it these histories, and they're not dependent on the future samples. Well, sometimes they do, but this is for modeling purpose. They use this assumption. Okay, and the theta denotes the parameter of the model. And then think about this: they are dividing the model into two parts, model A and model B. The model A meant the autoregressive model responsible for the long context learning. This one. So given a history of speech samples, what do they call this? Hidden variables. Or H high is defined as the output language model and a condition for diffusion. Yeah, output of the language model. Head, this is why it has the H, is abbreviation for head. And this is model B, meant this is a bidirectional attention. Yeah, it's no longer a single unidirectional attention. And so they can use the diffusion transformer, because diffusion transformer uses bidirectional attention. And so the generated, or the patch of speech samples that are to be generated, are dependent on the head. Okay. And this is a basic concept of it. And you can see the overall architecture. Let me move on to here, 3.1.2. This is why they mentioned in figure 1, the backbone of their system is a causal attention AR transformer. Like I said before, this is for speech generation. You can have a text condition as the initial input. For example, have a good day. And okay, they use text as a condition. Very interesting, right? And then they take the initial speech input. I would assume that they are using the registered voice of a person. For example, this is 3 seconds of voice, 10 seconds of voice as the kickstart or starting input voice. And then they're using aggregation encoder, which is probably like a stack of transformer layers, right? And then they get this input, but this is not the head. they're talking about. This might be a embedding I minus 2, and together with and then fed into this causal autoregressive transformer. And the transformer at this time point will output a head, which is a sub I minus 2. And then, okay. Yeah, this is what they're talking about, the single vector. I would call that EI minus 2, okay. And then they get H, okay. H is serving as a condition of the following distribution. Low LOCDIT. Well, you can see they are following this guy's work. And then after they get this, then it became a DIT. You're supposed to go from the HI minus 2, like they shown right here, this equation. I call this equation 2, okay? And this equation 1. And you can see getting the H minus 2 is all about P sub H of I is dependent on x1 up to xi, which is autoregressive model, right? This is why it's called autoregressive. This is AR model, okay, equation 1. And then when you get to the DIT, is all about how to go from the embedding, into the patches. So X I to xi plus p are given h sub I, right? And then after they generate a patch of speech, okay, they're gonna play this thing to the user on the fly, so they have a fairly low latency in terms of speech generation. And then they're gonna feed this speech back into the aggregation encoder again, so they would have EI minus 1. Then they repeat this process until the speech generation ends, okay? Because I think there could have a certain I mean, this is detailed. We can have certain control signal. If it output a end of speech signal, for example, they output some silence. Okay, the input will take. Okay, check. Okay, it is a pure silence for some time. If it yes, I will stop generating. Okay, or the model can keep running if they don't care about GPU cost. You can keep generating silence. But I believe you just send silence into it, it will still output silence. Okay, that's the general part of it. So I think the causal autoregressive transformer is clear to anybody. And also they're talking a little bit more about their lock DIT, which is about next patch bidirectional modeling. That's how they get the name from. It's called a local diffusion transformer, because you can see the transformer is no longer trying to generate all the speech, but they only generate a patch of it, only from I to I plus P, other than from I to I plus T. T is the total supposed duration of the speech. Okay. This would, I would say, this thing would significantly reduce the amount of computational resources involved in the diffusion transformer, because you only look at the patch other than the whole signal. So you remember that transformer complexity is O(n) squared, right? So the shorter the duration is, you can the more complexity you can reduce by having shorter duration into the input or the output. Okay. They propose this type of a context-aware diffusion approach. So the diffusion-wise, yeah, this is standard. I mean, but how to say this? There's not much to say about their diffusion transformer. I think that my comment on their diffusion transformer is they designed this thing specifically for speech usage. So they smartly, using the causal autoregressive transformer to get these either hidden embeddings or conditional vector H through streamingly process the speech data, and then using this hidden vector or head to generate patch after patch. So you can see the whole thing is significantly reduced in terms of the computational cost. And here they also mention about their LM guidance. So this is not new. Classifier free guidance, CFG, is used for enhance the condition adherence of generative model. And in diffusion, you can have two status, which is either unconditional or conditional. Okay. In their work, they're sharing the condition model. But let me start from what the image people are doing. Okay. First, because they're changing the order. So they first talk about what they're doing, but they later on mention that what people have done in the past. So in the past, these image people, they use a class label into the diffusion and apply CFG. What does that mean? So suppose they want to synthesize a picture of cat. So they would use for example, one hot embedding or some embedding vectors of cat. For example, they have a cat label. This is a cat. One hot impactor. So they concatenate this vector together with the H, which is the head of the hidden, the head of the input. Okay. How do you say that? What's the word for that? Or the hidden vector? I would call that hidden vector. They concatenate these things together, and you can see this approach lacks of generality, because you do have to know the class label of the thing you want to synthesize. But so if you want to use this approach, you would have to ask yourself, what is the class label for the patch of speech you want to generate? Is it a phoneme labels? Is a word? But it's super difficult for speech generation people to know. And then you have to model the duration, I think, because you want to see whether at this time point, whether this hidden vector is corresponding to some words that are being generated. For example, I have food today. So whether this current moment is related to food, this is super sophisticated. So, I mean, everybody wants a diffusion model, but they probably they don't want a class label. But in the past, people have demonstrated that after using class label and using this type of CFG, CFG set this H, with this H significantly enhance the performance. But in this DiTAR, they use a more generalized approach. They place all the conditions within the language model. So there's no class label, no phoneme label, no word label, etc. So just a simple H. But they do model the condition and the unconditioned. So the H can be either conditioned or non-conditioned, if that's clear to you. So this is why they have, where's the, yeah, this one, yes. See, so the epsilon is the something like a score in the diffusion model, and the Z is the noise, right? You want to have the noise, but the noise is sometimes it's unconditioned or conditioned. Well, this is unconditioned, right? You can see there's no H, unconditioned, and this is conditioned, and you have a this is omega W. Let's call that omega, okay? And this omega factor is controlling whether you prefer the condition or whether you give more weights to the condition or you give more weights to the unconditioned. But why? Why do people using these type of controlling factors here? But this is for more robustly generating the image or speech purpose. So when you have the omega equals to 0, that's the standard usage of it. But once you turn the omega less than 0, that means you want to have more weights for the unconditional cases. When you have omega greater than 0, you want this to have more conditions, or sorry, you have to have a greater weights on the conditional generation. Okay, this is supposed to be providing robustness reported in this paper. Okay, and this is why during training phase they have to train, or this is their design. I'm not sure whether this is the design they invented, because they say they can train the unconditional model and the conditional model together by sharing their parameters. Okay. The way they did this is by they occasionally omit the condition during training. Okay, this is why you can see this is the equation. Okay, makes sense. Well, the benefit of doing this, you can definitely see that is, imagine you train these two models together, and at the inference stage, you have to come up with the epsilon, theta, Z, and H, and epsilon, Z. Okay, you have to have two scores. But if you just train this model with some shared parameters, all you have to do is to only use the how do you say this? I think they mentioned that some way. Want to use the exact word they. Yes. Okay. So let's go back to here. And you can see they have this H here. This is not at the input level. It's at the decoder's input. You can imagine, okay, this is like a causal autoregressive transformer is together with its aggregation encoder. They're behaving like an encoder structure, right? Autoregressive encoder. And these can be viewed as the input to their decoder. So you can see you don't have to have train two separate models, and putting this only at the decoder stage significantly reduce the amount of training cost, and also, very importantly, inference cost. It's faster. Okay. And then for those of you who want to dig into the classifier-free guidance, I recommend you read this paper. And for those of you who want to understand more about the balance between the unconditional generation and the conditional generation in diffusion transformer, you should read this paper. Okay. And the temperature for continuous valued LMs. Yeah, it's continuous. This is some math. I would just also skip that. Which is not difficult to understand, but you have to understand. I don't have time today, but you have to understand. Okay, because diffusion model use ODE. I believe that I have a paper reading about the neural ODE. Search in my channel whether you can find it. Okay, implementation, I would also skip that because you might able to find some other people's implementation somewhere, because by then people, they might not release the training code because or they have, maybe they have, but they didn't share in this paper. Okay. Modeling diffusion information. I'm gonna skip that too. Zero-shot TTS. Yeah, zero-shot TTS. So yeah, they also wanna, like I mentioned, they wanna have a loss of telling when to stop. Okay, so they do have this in the what do you call that? Model that in the model, other than manually modeling that. Okay, they trained that stop model. Yeah, flow matching. Just search the keyword flow match or flow matching in my channel. I believe that I also have a paper reading on that concept, but I'm not covering that today. Yes. Regarding experiment, the setup, so they didn't use their own data. They're using LibriLight data and Amelia data. And they're also using open source data sets for evaluation, so people can replicate their work or their approach. And the metrics they use are word error rate of the synthesizer speech and the speaker similarity, which is not new if you listen to the paper reading of the Seed-TTS. And what is UT-MOS? Oh, they have also used automatically predicted MOS. Also, they compare the computational cost, which is flops. The results wise, I think this is easy to understand. On LibriSpeech, they have roughly the same parameters as other people. That's what they get in terms of word error rate. But similarity wise, this one's much better. The non-autoregressive and the UT-MOS is better, but they managed to bring the T-flops. For library speech test clean B, that many details. Well, the result is consistent. Okay. This is discretized NAR versus continuous AR, but that's not apple to apple comparison. I would say these two are kind of two comparable terms in the ablation study because there's only one AR thing changed. And you can see well, this is also confusing to me. I may dig into that later on because they say discretized modeling might be inferior compared to continuous modeling of the speech signal. But in terms of result, the discretized system get better result. Could that be the amount of data is not that much? Probably. This is my gut feeling. If you want to use a continuous model, you might want to have more data to train it because it definitely requires more parameters. This is my personal opinion. Want to see whether they covered these in their experimental results. Figure 2. Table 6, further detailed comparison model trained on proprietary data. Okay. Table 6. They're jumping to table 6 already. They do include their proprietary data. Oh, this is scaling. Okay. So when they have enough amount of data, I mean, ByteDance, they have lots of budget. Okay. They use these their own proprietary data. They can go, I think in the previous tables they use only about 0.4 billion parameters or 0.6 parameters. Now they went up to 1 billion parameters. What's the table? Where's table 6? Okay, yeah. This is a full comparison when you have enough amount of data, I guess. Oh yeah, this is why they have Seed-E and Seed Chinese. This is Chinese. This is on their proprietary data, but they didn't. I believe they do not mention how many hours of data they use. Okay, you can see it's much better. This is word error rate wise better, but it's not as good as their Seed-TTS. Okay, in the Seed-TTS, I believe that they have two versions. One version is a cascaded system, which is AR model plus DIT. And also in the Seed-TTS, they have something called a full DIT. And the full DIT is not like this one. This one is like a joint AR plus DIT. So the models might be different they're different in architecture. Okay, and you can see the Seed-TTS has the best how to say that, similarity for English and Chinese, but their DAR has better word error rate. I would like to see the mass scores, but there are no mass scores here. Temperature. Do they have where's table 6? This is table 5. Table 6. This is table 6 already. Okay. So most of these works, they are using discretized speech tokens. So you can see how you can obtain. Wait a second. I think this is not fair again because different systems are not trained on the same amount of data. Okay. Conduct tests on this. Yes. Well, there's a question whether they are trained on the same amount of data. Okay. So let's go back to results. They didn't mention, where do they mention their table 1 result? Let me see if I can search that. Oh, this one doesn't allow me to search table 1. Okay, just a subset of what the next figure 2 is about the performance of DiTAR consistently improved within either training data or model size, which is common sense, I think. Yeah, I want to mention their interesting thing. They have a sweet point in terms of the patch size. Yeah, so you can see, is it good to just have a patch size of just a 1 or a patch size of 8? And they tell you that, okay, if you like the similarity to be as high as possible, the WDR to be as low as possible, you should pick up a patch size of 2, which is kind of interesting. And they also play with the batch size. For NAR, non-autoregressive, the batch size, the throughput, this is about acceleration of the speed, okay. This is common sense. Scale of LM guidance. So without guidance is omega equal to 1. Okay. This is omega. So they don't want to, yeah, regarding the similarity, you don't want no guidance, which is like here, or too much guidance, which things would drop. But you want some guidance, which is here, right? And word error rate, well, you can see word error rate is keeping dropping unless you have too much guidance, I think. To me, either 2 or 3 are fine, right? But you also don't want too much guidance or no guidance. I still want to find the text of table 1. This is table 2, right? Table 1. Oh yeah, table 1 is here. They mentioned here as shown in table 1. 2 different configurations. Oh, that's it? Because I'm expecting them to discuss about the results in the table 1. Okay, that's what they're discussing about. They show strong, not the best, compared with NAR system. Yeah, it is the best, right? In this test, right? Where's table 1? No, it's not the strongest, not the best, because the discretized tokenization non-autoregressive model gets the best similarity score. Let's see what they say about this. They say strong, not the best. On par with NAR system. Well, they didn't analyze why. But they're just as awesome. Just mentioned that, okay, in terms of the mass score, they're doing better than the NAR, which is not true, I think. Oh, for test the clean B set, they're doing better than the NAR systems, right? But for the test A case, they're not doing better, right? See this? It's worse. Let's see this again. Right. They're mentioning this in another table. Okay. They're jumping from table 1 to table 2. Table 2 is located at here. Oh, this is interesting. So this is like automatic mass, or this is like human mass, or I assume this is a real human being. And the N mass means naturalness of the speech. Q means the quality of the generated speech. And S mass means S. Where's S? Similarity. I think this is called similarity, right? Naturalness, quality, or similarity, speaker similarity. Do you want to find out where is the S mass? Okay. Naturalness, quality, and speaker voice similarity. Okay. CMOS by side-side comparison with human audios. Okay. I think it's very difficult for people to rate on these scores, but CMOS people just give it. Oh, interesting. So you can see on these fine-grained tasks, let me know if I were wrong, okay? They should both found this one other than this one, right? Because the more score, the higher the better. This should be bolded, because okay, this should be bolded. Okay. Oh, they're saying what they're meant is, okay, this is human. This is the target speech. They're showing this as a base score. So this one is better than this and this. Okay, and these two systems are NAR systems. That's why they're saying this is a better. And this is better, yeah, for sure. They're doing better than the other two, E2-TTS and the F5-TTS. And the E2-TTS are here, F5-TTS are here, and they are both. Oh, they're both non-autoregressive, but using continuous. They're both non-autoregressive. So I do agree that according to their CMOS comparison, AR is better than NAR. But they, according to the results, according to the table they show in the table 2, they haven't demonstrated that the continuous speech tokens are better for modeling versus the discretized speech tokens. Because if you look at this, the discretized NAR is doing better than the continuous AR or the proposed method in terms of SIM score. And also for test clean A, the discretized NAR, although it with the inferior system, which is NAR, but with the discretized speech token, they can get better UTMOS than the continuous AR, right? See this? So NAR is worse, but the discretized in this way is way better than continuous signal, right? See these two. Although the word array is behind their proposed method. So I do think they need to have more rows, especially the discretized and then NAR. It's probably because even if the NAR is not doing well compared to AR, but when it integrated with discretized speech token, it will work better than the continuous autoregressive modeling. But the author didn't have that analysis about this. I'm expecting to see them to have more analysis about on these things. Yeah, the scaling behavior. Okay, once you increase the model size, you can see the word array drop and the similarity increase. Not very significant, very much. Is it significant? I agree. Historical context on some application study. That is I was talking about table 3 and table 3 and table 4. Okay, I'm trying to cover all the tables. Okay, impact of temperature on generalization diversity. Okay, I see that. Interesting to see. Efficiency. Well, I think this is their selling point because if you look at these results, they achieved a fairly good or strong MOS score while they have huge improvement compared to in terms of speed compared to the continuous AR system. Continuous ASR, continuous speech token plus NAR is very time consuming according to the results. You see this, and this. But if you're using a cascaded system, it's fast or even faster than their work. But the quality is not very good. So they would recommend you to stay away from cascaded system, but stick with continuous speech token and adopt their autoregressive plus diffusion network, diffusion model framework. Okay, I think that's about it. I would just try to dig into more works of the Seed-TTS because everybody right now can see ByteDance or TikTok's Seed-TTS provides or generates speech with very, very high quality, almost like a real human being, even with emotion. Okay. I wish you enjoy my paper reading, and if you do, please don't forget to hit subscribe and then turn on the notification bell. All right. I will see you next week. Goodbye.